Hello children, once again welcome back to Physics with Sanoop. See, in this video we will be discussing all the previous questions from the unit C, atoms and nuclei, and it is strictly according to the updated syllabus. So you need to expect only this type of questions for the coming examination. The radius of innermost orbit of hydrogen atom is 5.3 into 10 raised to minus 11 meter. What is the radius of third allowed orbit of hydrogen atom? See, this is the expression for the radius of the nth orbit. Okay, A0 is a constant and is called Bohr's radius. Okay, so see, third orbit means n equal to 3. So we will get this is 0.53 into 9, that will be see 4.77 angstroms, right? In hydrogen spectrum, the shortest wavelength in Balmer series. Balmer series means the series of spectral lines emitted by the electron when it makes transition from any higher level to the second level. Okay, Balmer series means so the shortest wavelength means the radiation of maximum energy. See, radiation of maximum energy in the Balmer series, that is a spectral line emitted when an electron makes transition to the second level from infinity. Okay, so R into 1 by 2 square minus 1 by infinity, okay, that is lambda. Then 1 by lambda dash will be, see, the shortest wavelength in the bracket series. See, Lyman means the final state will be n equal to 1. Balmer means n equal to 2. Electrons make transition to the second level. And Paschen series when electrons make transition to the third level. And bracket series when electrons make transition to the fourth level. Okay, so 1 by lambda dash, that is R into 1 by 4 square minus 1 by infinity. So here we will get lambda dash over lambda, that is equal to 4. So lambda dash equal to 4 lambda. Okay. Next, let capital R1 be the radius of the second stationary orbit and R2 be the radius of the fourth stationary orbit of an electron in Bohr's model. The ratio R1 by R2 is. See, radius of the nth orbit is given by Rn equals A0 n square. Then R1 by R2 is n1 square by n2 square, or second orbit and fourth orbit, so 2 square by 4 square, that is equal to 1 by 4, or it is 1:4. Next, let capital T1 and capital T2 be the energy of an electron in the first and second excited state. First excited state means n equal to 2, second excited state means n equal to 3. Of hydrogen atom respectively, according to the Bohr's model of an atom, the ratio T1 is to T2. See, energy of the electron in the nth orbit minus 13.6 over n square, that much electron volt. So T1 by T2 will be n2 square by n1 square, that is equal to 3 square by 2 square, or 9 by 4, 9:4, right? Then the total energy of an electron in an atom in an orbit is minus 3.4 electron volt. Its kinetic and potential energies are respectively. See, kinetic energy is negative of the total energy. See, total energy will be negative and its negative will be positive, or kinetic energy will be positive, and potential energy will be twice the total energy. Okay, here it's given that total energy is minus 3.4 electron volt. So kinetic energy will be 3.4 electron volt and potential energy will be minus 6.8 electron volt. So this must be the correct option. Next, the ratio of kinetic energy to the total energy of an electron in a Bohr orbit of hydrogen atom is. See, kinetic energy and total energy are of equal magnitude. Total energy will be negative, kinetic energy will be positive. Here we have to get the ratio of kinetic to total. So this must be 1:1. Okay. In the spectrum of hydrogen, the ratio of the longest wavelength in the Lyman series. See, longest wavelength means the radiation of minimum energy in the Lyman series will be one that makes transition from the Lyman series means second to the first. Okay, second to the first. To the longest wavelength in the Balmer series means the radiation of minimum energy in the Balmer series, that is from third to the second. Okay, third to the second. Okay, so here lambda 1 over lambda 2, that is equal to 5 by 27, we will get this one. Okay, Hydrogen atom in ground state is excited by monochromatic radiation of wavelength 975 angstroms. Number of spectral lines in the resulting spectrum emitted will be. So we have to find the level see into which the electron is excited from the ground state. See 1 by lambda, that is 1.1 into 10 raised to 7 value of Rydberg's constant, then 1 by 1 square minus 1 by n square, as the electron makes transition from the ground state to nth state. Lambda is given as 975 angstroms, means into 10 raised to minus 10. So here we will get, see if we simplify this, we will get n square equal to 16 and n equal to 4. So the number of possible spectral lines will be n into n minus 1 by 2 from nth level. So that is, if we put n equal to 4, we will get 6. Okay, this is the number of spectral lines. Then see, an electron in hydrogen atom makes a transition from n1 to n2, where n1 and n2 are principal quantum numbers of the two states. Assuming Bohr's model to be valid, the time period of the electron in the initial state is 8 times that in the final states. See, for an electron in hydrogen atom, the velocity proportional to 1 by n, where n is the principal quantum number, and radius of the nth orbit is proportional to n square. So the angular velocity will be omega equal to, that will be v by r actually, so it is proportional to 1 by n cube. So the period will be proportional to n cube. Okay, now T1 over T2, that will be n1 by n2 whole cube. So n1 by n2 whole cube, it is given as 8, or it is 2 cube. So we can say n1 by n2 equal to 2, or we can say n2 equal to n1 by 2. So n2 must be half of n1. See, n1 is 4, n2 equal to 2 means n2 is half of n1. This is true. Okay, that relation is not valid for any other option. Okay. Now the wavelength of the first line of Lyman series for hydrogen atom is equal to that of the second line of Balmer series for a hydrogen-like ion. Okay. The atomic number Z of the hydrogen-like ion. See, Rydberg's constant, Lyman series means electron makes transition from higher level to the first level. So first member of Lyman series means the electron makes transition from second to the ground level. Okay, so R into 1 by 1 square minus 1 by 2 square, and that is equal to the second line of the Balmer series for a hydrogen-like ion. See, Balmer series means the electron makes transition to the second level. Okay, and second member means from the third to the second, that is the first member, from fourth to the second, that is the second member of the Balmer series. Okay, so 1 by 2 square minus 1 by 4 square, and here we will get Z equal to 2. Okay, this one. Now ionization potential of hydrogen atom is 13.6 electron volt. Hydrogen atoms in the ground state are excited by monochromatic radiation of photon of energy 12.1 electron volt. According to Bohr's theory, the spectral lines emitted by hydrogen will be, see, 12.1 means the sum of these two, 1.9 and 10.2. So the electron is excited to n equal to 3. So the number of possible spectral lines will be 3 into 3 minus 1 divided by 2, that will be 3. Okay, so 3 spectral lines will be possible. Now an electron changes its position from orbit n equal to 4 to the orbit n equal to 2 of an atom. The wavelength of the emitted radiation will be, see, 1 by lambda, that is R, Rydberg's constant, into 1 by 2 square minus 1 by 4 square, that is equal to 16 by 3R. 16 by 3R. Then the energy of hydrogen atom in the nth orbit is E with the suffix n. So E with the suffix n is minus 13.6 over n square electron volt. Okay. Then the energy in the nth orbit of single ionized helium, that is E dash with the suffix n minus 13.6 Z square by n square. Okay, this minus 13.6 by n square, that is E with the suffix n, and Z equal to 2. So 2 square, that is 4. So 4En, 4En. Okay, so this must be the correct option. Next, when an electron jumps from the fourth orbit to the second orbit, one gets. Okay, fourth orbit to the second orbit means it is Balmer. It is a line from the Balmer series. Okay, so that is the second member. Okay, second member of the Balmer series, second line of the Balmer series. Now, which of the following transitions in hydrogen atom emits a photon of highest frequency? See, from n equal to 2 to n equal to 1, a photon can be emitted. But see, in this transition, when electron makes transition from n equal to 2 to n equal to 6, photon cannot be emitted. It will have to absorb a photon. Okay, and from n equal to 6 to n equal to 2, a photon can be emitted. N equal to 1 to n equal to 2, no photon can be emitted, but a photon should be absorbed. Okay, so we have to compare these two cases only. Okay, A and C. See, in the first case, when an electron makes transition from n equal to 2 to n equal to 1, the photon, energy of the photon h nu 1, that is 13.6 into 3 by 4. And when an electron makes transition from n equal to 6 to n equal to 2, the energy of the photon, that is 13.6 into 2 by 9. Okay, see, 2 by 9 means it will be 0.2222, and this is 3 by 4 means it is 0.75. Okay, so this one must be the photon with the highest frequency, this one. Next, in terms of Bohr's radius A0, the radius of the second Bohr orbit of hydrogen atom is A0 n square n equal to 2, so we will get 4A0, this one. Now, the ionization energy of hydrogen atom is 13.6 electron volt. The ionization energy of helium atom would be, see, energy in the nth orbit, that is minus 13.6 z square by n square, z equal to 2. So, it will be 2 square means 4 into 13.6, that will be 54.4 electron volt. Next, a nucleus of mass number 189 splits into two nuclei having mass number 125 and 64. The ratio of radius of two daughter nuclei respectively. See, a radius of a nucleus depends on mass number. See, and radius is given by r equals r0 a raised to 1 by 3, where r0 is a constant and is called a nuclear unit radius. It is 1.1 into 10 raised minus 15 meter, and a is the mass number. So, r1 by r2, that is equal to a1 by a2 whole raised to 1 by 3. And it is 125 over 64, that is 125, both 125 and 64 are perfect cubes. So, this is 5 cube over 4 cube whole raised to 1 by 3 will be 5 by 4, or we can say 5 is to 4, this one. Next, see, if radius of the aluminum 27 nucleus is taken to be r with the suffix al, then the radius of the tellurium 125 nucleus is nearly. See, again we have to use the same formula, then R2 by R1, that is A2 by A1 whole raised to 1 by 3, that is 125 over 27, this will be equal to 5 by 3. So, radius of the tellurium nucleus will be 5 by 3 times the radius of aluminum nucleus. Okay, this one. Now, let's see what we have next. If the nuclear radius of, again, aluminum 27 is 3.6 Fermi, the approximate nuclear radius of copper 64 in Fermi is R2 over R1, that is A2 over A1 whole raised to 1 by 3. This A2, that is the mass number of copper, that is 64, mass number of aluminum is 27. Both the numbers are perfect cubes. 4 cube over 3 cube whole raised to 1 by 3 will be 4 by 3. So, radius of the copper nucleus 4 by 3 times the radius of aluminum nucleus. So, 4 by 3 into 3.6, that is 4.8. Next, two nuclei have their mass numbers in the ratio of 1:3. The ratio of their nuclear densities would be, see, nuclear density is independent of mass number, or the density of all the nuclei are the same. Okay, so nuclear density will be in the ratio 1:1 only, right? Now, the radius of germanium nuclide is measured to be twice the radius of beryllium 9. The number of nucleons in germanium are, see, R equals R0 a raised to 1 by 3, or we can say mass number directly proportional to cube of the nuclear radius. Okay, So A2 over A1, that will be equal to R2 over R1 whole raised to 3. Okay, R2 by R1 is given as 2. So 2 raised to 3 means 8. So A2 will be 8 times the mass number of beryllium. That is 8 into 9, that is 72. This one. Now a nucleus represented by the symbol XZA has Z protons and A minus Z neutrons. So Z protons and A minus Z neutrons. Right? Now the atomic weight of boron is 10.81 and it has two isotopes. Boron 10 and boron 11. Then the ratio of boron 10 to boron 11 in nature would be. See, if we take a sample of boron, suppose the fractional mass of boron 10, let it be x, then the fractional mass of boron 11 will be 1 minus x. Suppose 2/3 of the sample is boron 10, then see 1/3 will be boron 11. If 2/5 of the sample is boron 10, then 3/5 will be boron 11. How do we get that 3 by 5 from 2 by 5? That is actually, see, if the fraction x is boron 10, then boron 11 will be 1 minus x. Okay. Now, how do we convert fraction to percentage? If fraction is multiplied by 100, you will get the corresponding percentage. Okay. Now, see, the weighted average is taken as the atomic mass. Okay. So, the fraction boron 10, okay, then the mass of boron 10, that is 10 AMU. Then 1 minus x is the fractional mass of boron 11 and the atomic mass of boron 11 is 11. Okay, this will give you the weighted average, that is 10.81. Okay, and see x you will get 0.19, means in a sample 19% of the boron will be boron 10. So the remaining, that is 81%, will be boron 11. So boron 10 to boron 11 ratio will be 19:81. 19:81. Now a nucleus ruptures into two nuclear parts which have their velocity ratio equal to 2:1. See, before splitting, the nucleus is at rest and its total linear momentum is 0. After splitting, it splits into two fragments of say masses A1 and A2, where A1 and A2 are the mass numbers, and suppose they are moving with the velocities V1 and V2. So the total linear momentum after splitting, that is A1 V1 plus A2 V2, that must be the same as the linear momentum before, that is equal to 0. So A1 V1 equals minus A2 V2, that negative sign is only to show that they are moving in opposite directions. So the ratio of their masses A1 over A2, that is equal to, see, I have dropped the negative sign because it is only to show that they are in opposite direction. Here we need only the ratio of their magnitudes. So it will be 1 by 2. So R1 by R2, that is A1 by A2 whole raised to 1 by 3, or we can say 1 by 2 whole raised to 1 by 3, or 1 by 2 raised to 1 by 3, or 1:2 raised to 1 by 3. The nucleus which has radius 1/3 of the radius of cesium-189. Now see, radius R equal to R0 A raised to 1 by 3, and R2 it is given as 1/3 of the radius of cesium, that 189. Okay, so A2 over A1 will be R2 by R1 whole raised to 1 by 3. R2 by R1 is 1 by 3 whole raised to 1 by 3 will be 1 over 27. A2 equals A1 by 27, 189 by 27, that is equal to 7. So it must be 1 with a mass number 7. Okay, so it must be lithium. Now see, a nucleus with a mass number 240 breaks into two fragments each of mass number 120. The binding energy per nucleon of unfragmented nuclei is 7.6 mega electron volt, while that of fragments is 8.5 mega electron volt. Okay, now see, the fragments, there are two fragments each of mass 120, so the total mass will be 120 plus 120, 240, and binding energy per nucleon is 8.5. So total binding energy will be 240 into 8.5. And initially the binding energy per nucleon is 7.6 and the mass is 240 AMU. So the gain in binding energy will be 240 into 0.9, that is 216 mega electron volt. So it must be 216 mega electron volt. Now the energy equivalent of 0.5 gram of a substance. See, according to Einstein's mass energy relation, energy equivalent of mass m is mc square, where c is the speed of light in vacuum. Here we have mass 0.5 gram, means 0.5 into 10 raised minus 3 kilogram, and c is the speed of light is 3 into 10 raised to 8 whole square. So here we will get 9 into 0.5, that is 4.5. 10 raised to 8 whole square will be 10 raised to 16, into 10 raised minus 3 will be 10 raised to 13. So 4.5 into 10 raised to 13 joules. The binding energy per nucleon of lithium and helium nuclei are 5.6 mega electron volt and 7.06 mega electron volt. In the nuclear reaction, see, a lithium 7 and see, we have a hydrogen nucleus, and see, it gets converted to 2 helium nuclei with the liberation of some energy. Okay, and we have to find the value of energy released. Okay, see, the binding energy per nucleon of helium, that is 7.06, and there are 4 nucleons in each helium nucleus, and such 2 nuclei are there. So 2 into number of nucleons in each nucleus, that is 4, and the binding energy per nucleon, that is 7.06. Okay, that is the total binding energy of the products. Okay, and initially, see, this is a single nucleus, there is nothing to bind. Okay, so no binding energy. And in lithium there are 7 nucleons and the binding energy per nucleon is 5.6. So this is 56.48 minus 39.2, that is 17.3. 17.3 mega electron volt. Next, a certain mass of hydrogen is changed to helium by the process of fusion. The mass defect in fusion reaction is 0.02866 AMU. The energy liberated per AMU is, that is, energy equals delta mc square. Okay, and energy will be 0.02866 into 931 mega electron volt. So see, you can consider this as approximately 1000. 1000 into 0.2866 will be 28.66, but this is actually slightly smaller than 1000, so the answer will be smaller than 28. Okay, see, the answer that is slightly smaller than 28, it is 26.7. Okay, 26.7, right, this one. Now the mass of lithium 7 and nucleus is 0.042 AMU, less than the sum of the masses of all its nucleons. The binding energy per nucleon. See, this 0.042 AMU is the mass defects, and the energy corresponding to 1 AMU is 931 mega electron volt. So the energy corresponding to 0.042 AMU is 0.042 into 931 mega electron volts. Okay, so that is the total binding energy, and binding energy per nucleon will be 0.042 into 931 divided by 7, that we will get 5.6 mega electron volt, this one. The binding energy per nucleon in deuterium and helium nuclei are 1.1 mega electron volt and 7 mega electron volt respectively. When 2 deuterium nuclei fuse to form a helium nucleus, the energy released in the fusion is. That is actually, see, in the final product, see, the binding energy per nucleon is 7 and 4 nucleons will be there in helium. So total binding energy will be 4 into 7. And initially, see, again 4 nucleons will be there. See, deuterium, 2 deuterium nuclei, so 4 into 1.1. So the difference is 28 minus 4.4, that is 23.6 mega electron volts. Now capital M, A, Z, then MP, Mn denote masses of nucleus, proton and neutron respectively in units of AMU. Okay, and 1 AMU is equivalent to 931.5 mega electron volt, and binding energy represents also in mega electron volt. Then see, mass of the resulting nucleus will be, see, less than the total mass of constituent nucleons by mass defects. Okay, so mass of the nucleus. See, this is mass of protons, then mass of neutrons minus binding energy divided by c square is mass defect. So this must be the correct option. Next, the binding energy of deuteron is 2.2 mega electron volt and that of helium is 28. If two deuterons are fused to form one helium, then the energy released is delta Q. This is the binding energy of helium, and two deuterons will have binding energy 2 into 2.2. So the difference will be 23.6 mega electron volt. Now see, in the reaction, see, H12 and H13 gives helium 24 plus a neutron. If the binding energies of H12 and H13 and He24 are respectively A, B and C, then the energy in mega electron volt released in this process. See, the final binding energy is C and initial binding energy is A plus B. So the energy released will be C minus A plus B, and that we can write C minus A minus B, this one.